Now, having taken a closer look at chemical shifts, let's ask the question, what else can we extract from the offsets that we measure as an oscillation in our free induction decay? For the ethanol spectrum, we also spoke about the fine structure splitting that makes the methyl group a 1:2:1 triplet and the methylene group a 1:3:3:1 quartet. Right now, we will focus on this parameter which is called scalar coupling. Before we venture close into this, I would like to revise very briefly the concept of chemical shift. I am sure you remember for a spin-half system characterized by the two nuclear spin states, the energy was given by minus mu dot B. Therefore, the Hamiltonian was written as minus mu dot B, which got reduced to minus gamma B naught Iz. So this will be called as a chemical shift Hamiltonian. So similarly, the Hamiltonian for scalar coupling, which I'll call the Hamiltonian of J, will be given by 2 pi JIS I dot S between two spins I and S. For instance, let's say we are taking an example of HA and HB. Let's say this is the I spin and this is the S spin. And as always, I will be given as IX I cap, IY J cap plus Iz K cap. So therefore, for a simple two-spin state system, your Hamiltonian will be given by the sum of the chemical shift Hamiltonian and the scalar coupling Hamiltonian minus gamma 1 minus sigma I B naught. Remember, I am including the shielding parameter since we have two spins times Iz minus gamma 1 minus sigma S B naught SZ plus 2 pi j is I dot s. So this can be rewritten as, I'm going to make a short form out of this so that it's easy for us. I'm going to call it omega I Iz plus similarly omega S Sz plus 2 pi Ij, where Jij is the magnitude of scalar coupling and I dot S is the dot product between the two vectors. You're going to have Ix Sx plus Iy Sy plus Iz Sz. Let's start with a simple case where the two spins that you're having are so far apart that their magnitude of scalar coupling is so small that to start with, you can say there is no scalar coupling between these two spins. So in which case, what ends up happening? Your Hamiltonian will be given by omega I Iz plus omega S Sc. So this shall be case 1 where no JIS, no scalar coupling between two spins. Since you have two spins here, you're going to have four states that end up coming: alpha alpha, alpha beta, beta alpha and beta beta. So let's go ahead and apply the Hamiltonian in the alpha alpha state. You're going to end up getting omega I by 2 plus omega S by 2. When you apply it on alpha beta state, you're going to get omega I by 2 minus omega S by 2. You might be a little confused on, oh, how come a positive value can have a lower energy? Remember, we set minus gamma B naught as omega naught, which is why you are seeing something of this sort, being the lower energy. And on top of it, how did I end up getting all this? When you have Iz plus Sz as the operator, Iz operates only in the first part and Sz operates only in the second part. So therefore, you are going to end up getting omega I times Iz on alpha will be omega I by 2. Omega S on Sz would be, Sz on alpha will be 1 by 2. So you get omega S by 2. Therefore, when the Sz operates on the beta state, you get a negative sign. So when you write it out, you're going to end up getting omega I plus omega S by 2, omega I minus omega S by 2, minus omega I plus omega S by 2, minus omega I minus omega S as the energy for these given four spin states. Now, if you want to think about transitions, you are able to understand the I spin is in the alpha state while the S spin transitions to plus minus, and in this case, I spin is in beta state and it transitions between S plus minus. Why don't we take the energy difference between alpha beta and alpha alpha minus alpha alpha? you're able to immediately understand when you take the difference, these two get cancelled and these two entities end up adding with each other. Therefore, you're going to get minus omega s. Similarly, let's try to take the energy difference between these two states, which once again looks at the transition of the s spin, which will be I request you guys to calculate the energy difference between these two states where it's I plus minus S alpha, I plus minus S beta. You would end up getting energy of beta alpha minus energy of alpha alpha will be minus omega I. So therefore, let's say we go to the rotating frame where all the omegas become capital omegas with respect to the omega RF, that is the transmitter frequency. You are able to appreciate the fact that either you get omega s, small omega s or small omega I. Therefore, you are going to end up getting a spectrum that looks quite straightforward. You are going to get one resonance at omega s and one resonance at omega I, depending upon what is their chemical shift. In this case, I am assuming the chemical shift of S is more downfield shifted than I, and I am plotting it in the ppm scale here. So, it's a very simple case where two spins that are not interacting by scalar coupling. How will its NMR spectrum? So, let's take another case where JIS is not equal to 0. In that case, let me rewrite the Hamiltonian. You had omega I IZ plus omega S SZ plus 2 pi JIS times IX SX. In this case, we will make a small approximation where the mod of omega I minus omega S, that is the chemical shift difference, or rather the shielding difference in this case, is much greater than the magnitude of scalar coupling between these two spins. This approximation is called a weak coupling approximation. This will be our case 2. In such a case, the scalar coupling Hamiltonian gets reduced to 2 pi JIS IZSZ, implying that the IX, SX and the IY, SY terms do not appear. Time being, please take this as a granted so that we can go forward and understand what ends up happening. So let's once again calculate what will be the energy of the alpha alpha state. Remember, now you have an additional scalar coupling component. So you're going to have omega I by 2 plus omega S by 2 plus 2 pi j times half, that will be 1 over 4. Similarly, how does the minus sign come here? Because one is in beta state, the other is in alpha state. When you have the IZ operate on the alpha state, you get half. When you have the SZ operate on the beta state, you get minus half. Therefore, you end up getting a minus sign there. Then the Hamiltonian on the beta alpha state, the plus comes here because you have two minus halves that multiply with each other. Therefore, you get a plus 1 by 4. So once again, let's do the same exercise that we did, which is calculate the energy difference between the alpha beta state and the alpha alpha state. Once again, this is the S transition because S goes from alpha to beta while I remains in the alpha state. This will be given by the difference between alpha beta and alpha alpha. So when you take the difference, you end up cancelling the omega I similar to the last time, but the other two terms get added up with each other. So you're going to have minus omega S, and remember you have this is 1 over 2, this is 1 over 2, and these two terms end up adding and you will end up getting minus pi j. So let's calculate what is the next transition for the same S spin, that is this spin, that is going to be given by beta beta minus beta alpha. I request you guys to repeat the calculation for the I transition. So let me redraw the spectrum that you had gotten earlier. Remember, we are going from small omega to capital omega, assuming we go into the rotating frame. And previously we saw the spectrum that looked like this, where there is no JIS. In this case, let's try to draw the same thing. you're able to understand omega s is further reduced and increased by pi j. So you're going to have 1, that is going to be, the difference will be 2 pi j. Similarly, you will have omega I, difference will be 2 pi j. The important aspect that you are able to see here is that one resonance splits into 2, therefore the sensitivity goes from 1 to half. Each of this resonance is 1 to 1, largely because the population in the alpha and beta states are very close to each other. Therefore, you get a nice 1:1 doublet. Similar would be the case for the I spin. So what you are able to understand is that if the I and S spin couple with each other, they end up splitting each other into 1:1 doublet. So this is the influence of scalar coupling, and more importantly, you will also be able to say this, the splitting between the resonances that you observe will be same for these two. The example that we just worked out is called the AX example, or we can also call the IS example. I request you guys to solve it for the AX2 system, where it's similar to IS2 system. I shall write the Hamiltonian for you so that it becomes easier. Remember, you have two of the same S spin, therefore they will have the same chemical shift. However, the J coupling between I and S would still remain JIS. So therefore, the Hamiltonian for chemical shift would be omega I Iz plus omega S Sz. The scalar coupling Hamiltonian will still be given by 2 pi j Iz Sz, where we are including the V coupling limit. The major difference that would come up between the previous case and this case is that you have 3 spins, where we can assume the first spin is I, the next two are S spins. You'd have different spin states that you need to interrogate the energy with. Get the energy for each of the state. After having determined the energies of these given states, see whether you are able to find that the I spin is no more a doublet, it will become a 1:2:1 triplet. Another example that I would request you guys to work out, and we can discuss further in the interactive session, is something called an AMX system. AMX system can be visualized of this sort: HA, HB, HC. You have HA that ends up interacting with HC, HA also interacting with HB, but HB and HC are not interacting with one another. So therefore, in this case, the Hamiltonian for chemical shift will be straightforward. You're going to have omega A Az, omega M Mz, and omega X Xz. On the other hand, the scalar coupling Hamiltonian will be 2 pi j AX, AM, let's say, because A and M couple with each other, times AZ Mz plus 2 pi j Mx, where M couples with X and with A, so therefore you're having similar system. So basically the small a is M here, given by Mz Xz, and you do not have a coupling term between the B and C protons, so therefore you will not have a term between A and X. Once again, you will have spin states that are given by these. Try to solve this problem as well, and you will be able to understand how this will not remain a doublet anymore. You are going to see further splitting. Also, just because two protons, which both are spin half, are coupling with this HA, you cannot say HA will be a triplet, and you will see that the magnitudes of JAM and JMX will determine whether it will be a triplet or a doublet of doublet. Yet another example that you could try to look for is one where AMX system, where you have JAM, JMX, which was the previous case, and in addition you also have JAX coupling. Apply all these cases to understand how scalar coupling nicely helps you get the fine structure information on the chemical that you're trying to probe. And of course, you will be able to see when you go from IS, IS2, IS3, you will be able to build up the Pascal's triangle that we had seen. Before I finish up the entire discussion on scalar coupling, I'll also give a little bit of intuition how scalar coupling is useful. Similar to the fact that the electronic environment can be deduced from the chemical shift that we measure, the scalar coupling would help you in a way where, let's say you are having two atoms, let's say HA and HB, that are interacting through three bonds. The scalar coupling that you end up measuring, so for the sake of simplicity, I'm going to write NJIS, where N stands for the number of bonds, IS stands for the spins that end up coupling, would be given by a Karplus equation for N equal to 3, given by A plus B cos theta plus C cos 2 theta. So given that you are able to measure the scalar coupling, you would actually be able to say what is the dihedral angle between these two protons. So this is what gives NMR an immense power on the fact that the magnitude of couplings would help you understand which spins are coupling with one another. And on top of it, the magnitude of coupling could also be interpreted for certain cases using the Karplus equation, which helps you further determine structures for molecules. To summarize this lecture, I would like to take you back to the oscillation part, where you are able to see when you are able to get the oscillation, you would be able to pick up what are the chemical shifts. And this oscillation also comprises the information that you want to get from scalar couplings. We saw an example of the AX or the IS spin system, and of course solve the other examples for AX2, AMX. In the next lecture, we will be taking a closer look at this parameter, which will be the relaxation parameter.